Good afternoon, everyone. Thank you for being here. I'm Duan Liang, and from CRC Changchun Railway Vehicles Corporation. Here, the title of my presentation is Influence of Service Environment on the Welfare of High-Speed Trains. You will see 4 parts of the presentation. The first is background, the second is overview of the analysis procedure. The third is factors of service environment, and the last is a novel wheel profile. Firstly, please allow me to briefly introduce our corporation to you. It was founded in 1954 and has 14,000 staff. It engaged in development, production, and maintenance of high-speed EMU mainline passenger vehicle, urban mass transit vehicle, and other products. Its annual production capacity is 1,000 high-speed EMUs, 1,200 urban mass transit vehicles, 500 mainline passenger vehicles, and 6,000 bogies. Those pictures, those pictures show the according products, and this is the red orange line of Boston Metro in America, and this is the double-deck passenger vehicle in Australia, and so on. Now, let's go into the topic. So far, Chinese high-speed railway has exceeded the total mileage of high-speed railway has exceeded 25,000 kilometers, and about 3,000 EMUs, including Chinese standard EMU, which completely designed by China, has been put into the daily operation. However, the service environment of Chinese EMUs is quite complex. Like the operating distance in a single day can be 2,000 to 3,000 kilometers, and the weight and the temperature of weather in 1 year could be changed from minus 40 degrees Celsius to positive 40 degrees Celsius, and the difference of rail maintenance, and so on. Based on these facts, we must study the characteristics of welfare of high-speed EMU, because it almost decides the dynamics of high-speed EMU. For the characteristics of welfare of high-speed EMU, it's very difficult to predict totally by simulations or bench tests. So we conduct lots of on-track tests and collect all records of wheel reprofiling in the past several years. Besides, we develop wheel analysis software to utilize this data efficiently. And here, I will show these factors of service environment in detail. The first factor is reprofiling cycle. The test lasted for 2 years, and the EMUs The test lasted for 2 years, and the EMUs operated in the northeast of China. The lowest temperature in winter could be minus 40 degrees Celsius. We found that the tread wear is about 0.25 to 0.4 millimeters per 100,000 kilometers, and the increasing rate of equivalent condensity is about 0.08 to 0.1 millimeters per 100,000 kilometers. With the total mileage increasing, the wear rate may be different in each one reprofiling cycle. The second factor is operating speed. We chosen 2 kinds of operating speed for the EMUs which operated in the same line. The results showed that the tread wear of operating speed at 300 kilometers per hour is slightly larger than that 350 kilometers per hour. And the equivalent conicidity of operating speed at 350 kilometers per hour is slightly larger than the speed of 300 kilometers per hour. The next factor is the different season. According to the whale reprofiling data of 30 EMUs which operated, which have the same whale profile, the results show that the cheetah whale from May to September is slightly larger than that in other months. In other words, the cheetah whale in summer and autumn may be slightly larger than that in spring and winter. Similarly, the equivalent conicity at summer is larger than that at other seasons. For the EMUs operated in the north, we found that the equivalent conicity of motor bogie is larger than that of trailer bogie. The next factor is different track condition. We must realize that different track may meet different whale profile because of the different maintenance principle in China. The difference may be result in different maximum worm position on treat. It's found that the real whale profile is the real whale profile may be higher or lower than the standard profile. The former one and the latter one occurred by before grading and after grading respectively. For the two mirrored profile, the maximum worm position is different. Once maximum worm position locates in the outside of the nominal rolling radius as depicted in the blue curve. Once position locates in around the nominal rolling radius, which described in red curve. Besides, we found that once the EMUs change its operating line, it may easily cause the hunting movement of bogie because of the adaptation of whale-whale contact. The last factor is whale diameter. After tracking different EMUs which operated in different lines, we found that the whale will increase faster as the whale diameter decrease during one reprofiling cycle, different whale diameter. And the surface hardness on whale tread decrease as the whale diameter decrease. The last part is a novel whale profile. Through analyzing those massive data, our novel whale profile has been put forward by us. It has been applied on Chinese standard EMU since 2017. Its behavior has demonstrated that it could improve the whale-whale contact geometry and extend the reprofiling cycle to 1.5 times of original profile. And the whale-whale rate is comparable with original profile. Okay, my presentation is over. Thank you for your listening.
You give the real data of the wheel. Okay. Any question for this paper? Any question? Yeah.
Thank you for the presentation. Which was the reason for changing the wheel profile, or which was the reason for reprofiling the wheels before the change of the profile was done?
You mean the reprofiling data?
Yes, you have changed the wheel profile. So why did you change, or what was your goal with this profile? Why did you choose this shape of the profile? In the last slide, I think.
Is this?
No, the last one, I think.
Okay, here?
No, the last of the presentation.
Okay, the next.
This one.
Okay, there.
I understood that you choose the red wheel profile.
Okay, I know. You mean they extend the reprofiling cycle to 1.5 times of original reprofile? Okay. Here maybe I don't show the evidence it's actually extend the reprofiling cycle because the conclusion is based on our operating data. This I don't show it, but
you got it with this profile by changing the wheel profile from the black one to the red one.
The red one to black one, yeah.
From the black to the red one.
Yeah.
No, the red one is the new profile.
Here. The black one is a new design, and the red one is original.
Hello,
Okay.
and I can explain it. Why? Because in our operation, we faced some dynamic problems like hunting, like bogey hunting, because the original profile is not suitable for the different real profile in the maintenance circles. So we have to design a new real profile.
Okay, understood. Thank you.
Okay, thank you.
Okay, we still have 1 minute.
Okay.
1.5 minutes. Yeah. Okay.
I have one question about profile design also. It was a good question about new design and tall profile. When you designed your new profile, have you considered curvature of the track, or also have you considered, do you have different rail profiles for curves? Because what is your optimization techniques? You use one profile for tangent track, rail profile, and you use different profiles for curvature. For curved track.
For curved.
So how you optimize this profile?
Okay, you mean the new designed profile?
Yeah, a rail vehicle always has wheel profile. It's no problem. So you install wheel profile, or not install, you install wheel with wheel profile. My question is, because on railway track we use different profiles for tangent track, and we use different rail profiles for curved track. So in your case, when you make decision on your profile, how track location was considered or something like this?
Okay, I know you, what's your meaning, but the new designed profile is based on is not completely by the maybe there is some experienced factor in this design.
No,
With all
you consider that, I think this is for high-speed train in China.
Yeah.
So for high-speed train, the curvature is very large, similar
But
to the
you
straight.
You still use different profiles.
No, same profile.
Or on the curve track and on tangent track.
The same one for the straight track and for the curved track. Because the curved track is very large, it's similar to the straight track. Is that true?
Yeah.
Yeah, okay. This is the answer. Okay.